Hello everyone, welcome to Code Enzyme. In this video, we are going to discuss the problems of Codeforces around 1000 Div2. And so we will be discussing all the problems from A to E problem. So I did miss this contest because of the unusual timing, but yeah, I did Upsolve till the E problem. So let's discuss them one by one. Okay. So for the A problem, let's first read the problem statement. A segment of positive integers L, R is called coprime if L and R are coprime. Basically, we don't really care about the numbers between them. We just care if L and R are coprime. So this segment is also called coprime. Okay. A coprime segment is called minimal coprime if it does not contain any coprime segment equals to itself. Okay. To better understand this statement, you can refer to the notes. We need to find the number of minimal segments contained in L, R. So since this is the A problem, I will not discuss much about it, but what this basically means that if you have an L, R, it is clear that L and L plus 1 will have a GCD of 1, right? So I mean, even if you don't really understand the problem statement, if you just try to find try to see the sample test cases, like it is simply x minus r minus l for this test case. For this test case also it is r minus l. For this test case also it is r minus l, and these two have one thing in common, that is l and n plus 1. So if r equals to l plus 1, l and r are already a minimal coprime. So in that case we will have an answer of 1. Okay. So the logic is pretty much simple, that if you have this condition, the answer is 1. If you have L equals to R equals to 1, then also the answer is plus 1. Otherwise the answer is simply R minus L. Okay. And how can you get, like, why is this R minus L? Because all the pairs of L and L plus 1 will be minimal coprime. Okay. So this will be one pair. This will be L plus 1 and L plus 2 will be one pair, and this goes on till L R minus 1 comma R. So if you count how many numbers are there, it will be equals to R minus L. So these are the number of pairs that are minimal coprime. Okay. Yeah. So let's move on to the next problem, or if you want to see the code, I will also show you the code. So yeah, just check if L plus 1 equals to R, then the answer is 1. If both are 1, then also the answer is 1. Otherwise the answer is simply R minus L. Okay. Let's move on to the next problem. Okay, so let's see. Okay, for those who have not read the problem statement, you are given an integer sequence A from A1 to AN, so it is 1 based indexing, and a segment L to R. Okay, you must perform the following operation on the sequence exactly once. So we can choose any subsequence of A and then we can reverse it. Okay, note that the subsequence does not have to be contiguous. And yeah, so we need to find the minimum value of AL plus 1 till AR. Okay, now how can we actually go about this? Now yeah, let's quickly see this also. So you have n numbers from A1 to AN. So let's say, okay, so let's say A1, A2, A3, and you have AN, right? Let's take okay, so let's take a few more numbers. So AN minus 2, AN minus 1, and AN. Okay, so 1 based indexing, and you also have a range, let's say from here. So let's make this AL to, let's say, some AR. Okay, and you need to take a subsequence. Now subsequence means that you can skip some of the numbers easily, and it doesn't really matter if it is contiguous or not. You can select any subsequence and your answer will be there. Now does it really, like, if you select A2 and AN and reverse it, these two numbers will be reversed, but it will not really affect my sum, right? The sum of these numbers, it will not really affect. So I can always select a smaller segment. So it is not really worth selecting two numbers from such that they are from the left side of L or they are both from the right side of R, right? So yeah, what you can do is, let's say, that's what I thought was, let's say you have a range like this. So you have a range A1, A2, then you have AL plus 1, and then let's say AR, and then you go till AN, right? So what you can do is, there are two ways to actually minimize the sum of this range, right? One way is to simply move a smaller number in, right? So we can try to move a smaller number inside, or second way is to move a bigger number outside, right? So the second way is to simply move a bigger number out this range, okay? And since like before also, like we can't select two numbers from both here or from both there, it is always so we can actually operate in like this, either in this range or we can operate in this range, okay? Now let's say you have a number, let's just take an example. Let's say you have A1, A2, A3, A4, A5 and A6, okay? And this is your this is your segment like L to R, okay? Or maybe we can take something odd, that will be a better example. A7. So let's say these are even numbers. So this is my L, this is my R, and let's say these are the minimum K numbers. So these are the minimum 4 numbers, right? So this is the minimum. Let's say A2 is the smallest, then comes A4, then comes A3, and then comes A6, okay? So we have the sorting order. I'm taking a random sorting order, it is not something I have already thought of. So A2 is the smallest, then comes A3, then comes A4, then comes A6, then comes A1, then comes A5, and the biggest is A7, okay? So what you will realize, like, there will always be some way possible that I can move these 4 in. Like currently we have this, so what we can do is we can select a sequence like such that the A7 is at the largest, A2 is at the smallest, so these two will be swapped. Then I don't want to swap A3, A6, right? I don't want to swap A4 because it is already in the range. I can choose the second number to be A5 and the third number to be A3. So these two will get swapped, and these two will get swapped, and easily A2 and A3 will move inside this range, and there will always be a possible way so that you can have these 4 numbers inside your L2R. Also you can try something like AL plus 1 till AR, and till goes till AN. And if you see in this range, if you have you can try to find the R minus L plus 1 smallest number, and there will be always some way that if you reverse, you will always be able to get these many numbers from the right hand side inside your range. So you can try both these possibilities to get these numbers into this range, and just take the minimum sum of it. So that was the explanation, and let's see the code. Okay, so what we are trying to do is, okay, first of all I am making it zero based indexing because that will be easier to process. Then let's take the integer array, and yeah, so what I am doing here is I am making a separate array for all the numbers from position 1 to position R, and then there is a separate array for position L to position N, like the last position, and now we can sort them, okay? And since I already told you, there will be always let this number k is equals to R minus L plus 1, there will be always some way to get these smallest numbers in the range. You can calculate, like, okay, sorry about that. Okay. So since there will be always some way to get these many numbers into the range, you will always have these many numbers in the range. You can just calculate the sum of first these many numbers and just take the minimum out of them, and that will be your answer, Okay, so I hope that makes sense, and let's move on to the C problem. Okay, you are given a tree of n vertices. You must perform the following operations twice. Select a vertex V, remove all the edges incident to V, and also the vertex V. Please find the minimum number of connected components after performing the operation exactly twice. Okay, so the thing is, what you need to do is, let's say we have some tree-like structure. So you have 1, 2, 3, um, let's say 4 and 5. So clearly it makes sense that you can destroy this 2, and you will have 4 connected components, right? So yeah, oh sorry. Okay, so let's first discuss the sample test cases for those who have not actually solved this till now. Now, like 1 and 2, there are only 2. You will delete these 2 nodes. You will have no connected components left. For 4, we have 1, 2, 2, 3, and 2, 4. So let me just draw this. So we have 1, 2. Uh, you will have 2, 3, and you will have 2, 4. Okay. So in this case, it clearly makes sense to destroy the 2 part because it is connected to maximum. So I can destroy this 2, and let's destroy one more. So we will have 2 connected components left. So that is why we have the answer as 2. And in this test case, like 1, 2, 1, 3, 2, 4. Okay, let me erase everything. So we have 1, 2, 1, 3. Then we have 2, 4, 4, 5, 5, 6, and 5, 7. Okay, so the one with the highest degree that I can see is clearly 5. So it makes sense to delete 5 first, right? So because that will increase the maximum number of connected components. So yeah, and the second node that I can delete is either 1 or 2 because they have the maximum degree right now. So let's delete 2. So we have 1, 2, 3, and 4 connected components left. So that is the answer. Yeah. Okay, so from the sample test cases, like you might have come up with an idea that it makes sense to delete the like the first move. It makes sense to delete the node with max degree, right? Yeah. So, but there is one problem. What if there are many nodes with the same maximum degree? Then that in that case we have to handle, and I will discuss about that a minute later. And the second node, what should you do with the second node? Now let's first discuss this case first. So which node should we select as our second node to delete? You may argue that you should select the one with the max degree, but that is not really the case. Why? Because let's say you have 1, 2. I mean, I will give you a better way. I mean, this is what that was in the editorial. So yeah. So when we are deleting this, let's say we select this node as the one that we want to remove. Okay, so this was the maximum degree node, let's say, and I mean, let's forget about the max degree node. Let's see what happens when we delete any 2 nodes. How many connected components are we getting? So if I mark the number of connected components, like what is the degree of each node? This is degree of 1, this is degree of 3, 1, 2, and 1, right? So whenever we are deleting any node, let's say we are deleting this node, how many connected components are we getting? If I delete this node, I am getting 2 connected components. Let me write it with the red color, right? When I am deleting this 2, actually not even 2, I am getting one single connected component, right? When I am deleting this 2, how many connected components am I getting? So 1, 2, 3, and 4, -1, so I'm only getting 3 connected components. Similarly, if I delete this 2, so 1, 2 and 2. Yeah, because when I delete a node, it is also removed, right? So that is why like this edge is dividing this whole graph into 2 connected components, because every edge is a bridge. It will divide the whole graph into 2 connected components, but we are also deleting the node itself. That is why it will decrease the number of connected components. So what I can say from here is deleting one node will give the degree of the node uh, connected components, right? So that will improve my answer. But what happens when I delete another node, right? So let's see, and let's take the same graph. So we have 1, 2. I will take a smaller graph this time. So, okay, these have degrees 1, 2. I mean, actually, let's take one more. Where is the pen? Sorry about that. I will change the color. Yeah. So we have 1, 2. Actually, this will become 3. 1, 2, and 1. Okay. Now what happens? Like, let's analyze by different pairs. So I mean, it is quite obvious. Let's take first number as this one and second node as this one. So how many connected components will we get if I remove these two nodes? So I will get 3 connected components, right? What happens when we delete this one and this one? So I will get 1. In this case also we will get 3 connected components. What happens when we delete these two? So this is for 2 and 4. This is for 3 and 5. And this one is for, let's say I delete these two. So 1, 2 and 3, right? This is for 2 and 3. So what you will realize, like if these two are connected, okay, like if these two, like 2 and 4 were not connected, so the answer is simply 3 plus 1 minus 1. So that is the degree of 2 plus degree of 4 minus 1. If 3 and 5 are not connected, so it is 2 plus 1. Okay, let me think about this. 1. Okay, it should be 2, not 3. Yeah. And for this one, 2 and 3. If you delete these two, you will get 3 components. So degree of 2, which is 3, plus degree of 4, which is degree of plus 2 minus 1, which is 3 plus 5. Answer should be 4, not 3. Let me think. 1, 2 and 3. It should be 3. Okay, so if they are connected, like if these two are connected, we can't have there should be -2. Why? Because let's say these two graphs are connected. um, um, this has node u with degree d1, this is v with degree d2. Okay, deleting this node will produce d1 components, deleting this node will produce d2 components, right? But we have a common link here. So because of that, it will produce a -2 sign, because the node itself and these two will produce a -2 sign, and that is why we are getting this formula d1 plus d2 minus 2. Okay, I mean, you can even like do this with an example. Let's say 4, 5 and 6. How many components? Like this has degree of 3, this is degree of 3. When you delete these two, the 3 plus 3 minus 2, right? So that is 4. So when you delete these two, you will have 4 connected components. 4 connected components, 1, 2, 3 and 4, right? Yeah. So now what you can simply do is like obviously first thing you should do is select the maximum node with the maximum degree. Right, just select the one with the maximum degree. Then for just loop for all the other nodes, like for 1 to n. Okay, check how many connected components you will get if you delete this node and this node, okay, the second one, and just take the maximum of it. Now there is one problem though, that happened because which I got when I was solving this problem. I got a lot of wrong answers. Why? Let's say you have something like 1 2 3 4 and 5, okay. Now clearly, like if you count the number of degrees, this has degree 2, degree 2, sorry, this is degree 1, degree 2, degree 2, degree 2 and degree 1, okay. Now it makes sense to take the first node as the maximum degree. You can take this node also, you could have taken this node also, you could have taken this node also. Yeah, so what we can do is there are a lot of candidates, right? But if by mistake you selected this node, like this one, and you deleted it, um, you will be left with how this one 2 and 1 and 4 and 5, right? And then you can delete any of the node, you will have at most 2 connected components, which is wrong, right? Because the optimal way to do this would be 3 2 and 1, 4 and 5. Optimal way is to delete one of the two nodes, that is 4 and 2. So let's just delete that. Yeah, and then you can delete one of these two nodes, so you will have an answer of 3, right? So what you can do, like if you have multiple nodes, the final solution would be, if you have multiple nodes with max degree, then try at least 2 of them, right? Yeah, so that kind of completes the solution. I will just show you the code now. Okay, so first of all we will create a graph, obviously. Then what you can do is, okay, you need to increase the degree. We will calculate the degree of each node, and after that we can find the node with the maximum degree. And yeah, since we want to find the number of nodes that have maximum degree, I will traverse them again and create a vector of those nodes that have the maximum degree, okay. And then like you can try any of the nodes, and maximum you need to just try 2 of them. You don't need to go for all the nodes. So let's take one of the nodes, and in that you can just find out the how many of the nodes were connected, and like you can make the make a boolean vector of if these two are connected or not. And if they are connected, so there will be a factor of -1 more, otherwise it will be like degree the sum of degree -1, and if they are connected it will be -2. Just take the maximum and just try to maximize your final answer. Yeah, now let's move on to the C problem. Okay, now let's move on to the D problem. Game with triangles. Okay. Okay, so there are n plus m distinct points, a1 comma 0, a2 comma 0 till a n comma 0. Then we have b1 comma 2, b2 comma 2 till bm comma 2. Initially your score is 0. You try to increase your score, you can perform the following operations. You can choose 3 distinct points which are not collinear and increase your score by area of rectangle formed by these 3 points. Then erase these 3 points from the plane. Now Kmax be the maximum number of operations that can be performed. For example, if it is impossible to perform any operation, Kmax is 0. Okay, so if we cannot perform any of the operation, then Kmax is 0, and we define Fk as the maximum possible score achievable by performing operation exactly k times. So yeah, and let's see what this says. First of all, it is given like what is Fk. So Fk is, okay, it is not like Fk, it is Fk is equals to maximum possible score by performing k operations. Okay, and we must perform exactly k operations. We can't go k minus 1 like that. Now we need to print fk values for all the k integers. So somehow we need to calculate this, and we need to calculate, like, let's say k can go till 2 into 10 to the power 5, right? Like, what is the maximum value of k that can go? uh, like, let's say you have n, and let's say you have m points. So clearly the total number of points is equals to n plus m, right? So at the max level we can have divide by 3. So this is the maximum the k can go. I don't think it can exceed this point, obviously. Now yeah, okay, let's try to see the sample test cases. I think this one works. So we have one line. It is 0 comma 100. So at one point we have 0, sorry, at one point we have 0, and then we have a point on 100. Then we have another point. These are like 2 units apart. This is minus 100, minus 50. So we have minus 100, minus 50, 0, and 50. Okay. So obviously, since area of a triangle is half into base into height, since height will always be 2, you can just subtract it. And this base is simply, you can choose 2 points from the same line. So I can choose 2 points from up also, I can choose 2 points from down also, right? So it makes sense to always choose the farthest point, because that will give me the maximum base. So yeah, I can choose like 150 and like that. So this is quite easy. Like, you can choose the maximum, you can put these values in a multi-set, right, to always get the farthest pair of points, right? So this will always give you the farthest pair of points. One, you can just get the integer at the start of this multi-set, and other point you can get the integer from the end of this multi-set. But and if the above line has only 2 integers, you can select any one of them, and yeah, like that. But what happens when there are more integers? Let's say the above line has integers like from a1, a2, a3 till, let's say, an, and the below line has a lot of integers like from b1, b2, b3 till bn. Okay. Now clearly, from one of the lines, let's create a multiset on this. You can what I was trying was I was trying to create a multiset on this, and we can also create a multiset on this. And these two multisets, from these two multisets, I will always have a pair of maximum farthest pair of points, right? I can try to calculate the value of a1 minus an and b1 minus bm, and whichever is maximum, that will become my base. And but the point is, which point should I take from the above, like from the other line? Should I take a1, should I take an, or should I take something else that will maximize my answer? So what the conclusion was, I should take the closest one of the points that were closest to each other, because removing them will increase my answer, increase the length of the base, right? Yeah, I should not consider taking a1 and or an, because this is my farthest pair of points. I should always try to take one of the closest pair of points, right? So this is the closest pair of points, and similarly I need to maintain that in the lower order. But we don't know any data structure that will help me maintain the closest pair of points. At least I don't know, that can help me maintain the closest pair of points in like this. So what can we try? So the editorial solution goes like, I had to see the editorial for this one. So the editorial solution will go like, let's say you want to calculate fk. Okay, and it is not easy to see like how many out of these operations, let's say p operations were made on line 1 and let's say q operations were made on line 2. Okay, so this is line 1 and this is line 2. So p operations were made on line 1 and p operations were made on line 2. Okay, so let's define like g of k, g of p comma q. So fk is g of p comma q such that p plus q equals to k, and we need to calculate this, right? And let's define the points like capital A1, capital A2 till AN. So these are in some sorted order. Like the previous one were not in sorted order, now we have sorted it. Okay, so let's say we have B1, B2 and BM. Okay, yeah, so we have this. So since p plus q equals to okay, let's keep them as p and q only. Now if I am performing p operations on line 1, right, so that means after p operations I will have removed 2p points from here and p points from here, right? I will when I'm performing p operations on line 1, I have to remove 2p points from line 1 and p points from line 2. Similarly, I have to if I'm performing q operations on line 2, I have to remove 2q points from line 2 and q points from line 1, right? So one of the constraints are simply like 2p plus q should be less than equals to n, and 2q plus p should be less than equals to m. So these are the two constraints that we need to take care of while solving this problem, right? And also we have one more constraint, that p plus q equals to k. Now let's say we have fixed a k. So we have fixed my a k value, it is some k value. We need to determine what should be the p and q value, like out of these k operations, how many operations do I need to perform on p line 1, how many operations do I need to perform on line 2 to get the maximum answer. And for that we need to find out the function of g of p and q. Okay, so let's say these are valid operations, like if you have these kind of operations, so let's say these are valid operations. So how many will we have? Like if I'm selecting p points from this line, it is obvious that I should select a1 and an as my first pair of point, a2 and an minus 1 as the second pair of point, and so on, right? Because that will maximize my base. So for p, what my answer will simply be equals to I equals to 1 from 2p a of, now it depends if you are taking 1 based indexing or 0 based indexing. If you are taking 1 based indexing, it will simply be n minus I minus a of I, right? Plus now that you are taking like that, so I equals to 1 to q, it will become b of m minus I, sorry, there should be a plus 1 also since these are 1 based indexing, minus bi, right? So this is the value of g of p comma q. Okay, now yeah, so if I give you a p and q value, you should be able to calculate this sum, right? In it will take you big O of n time, right? So you can actually use prefix sums to do this in big O of O1 time. Okay, so just calculate a prefix sum of these a and b values, arrays, and you should be able to query these values in big O of 1 time, right? Now like what you can do is, I mean, you can actually break it like from ai from backwards, and then you can do some maths and do it. For me, I will just show you how actually I did it, but yeah, we can actually find g of pq in big O of 1 time using prefix sums. So I will also write it here. So prefix sums. Now since we have this, what else that we can do? Let's try to solve some do some algebra on these points and try to find the range. So since p plus q equals to k, maybe what we can do is we can replace q as, since p plus q is k, we can replace it by, we can say like, okay, let's say p equals to x and q equals to k minus x. Okay, and when we have this p equals to k and q equals to k minus x, you can try putting it in these equations and reduce this from two variables to one variable equations. So we have 2p plus q less than equals to n, right? So first equation, like this was my first equation. Second equation, let's say it was 2p plus q less than equals to n. So for this we can use these values. So 2 times in p 2x plus k minus x is less than equals to n, and from here we will get x is less than equals to n minus k. Okay, so this was one of the conditions, and in the second condition, let's use this equation. 2q plus p is less than equals to m. If I put in all the values, 2 times k minus x plus x less than equals to m, and this value will become 2k minus 2x plus x less than equals to m, and this is minus x. Okay, so x is greater than equals to so it is m minus 2k, right? Yeah, so this is another condition that we have. So these are the number of x is basically the number of operations that we are performing on line 1, right? So these operation, obviously let's see if I had any other equations. No, but obviously there will be more constraints, like x has to be, like, since x is greater than equals to this, it can happen that 2k value is much greater than m, right? So let's have one more condition, that x is greater than equals to 0, and obviously if x is too small, I should have one more conditions, like condition that obviously since x plus y, x must be less than equals to k. I can't go more than k operations, right? Yeah, so like that. And now from these equations, like if you see, what do we have? So we can combine these equations, like x is less than equals to this, so x is actually less than equals to minimum of these two things, that k and n minus k. Sorry about that. So we have k comma n minus k, and in this case, since x is both of these are greater than equals to 0, we can combine this and make it like max of 0 comma m minus 2k, right? Yeah, so we have this, and when we have this, like so like if you have some l less than equals to x less than equals to r, the number of terms, like the number of possible value of x is simply r minus l plus 1, right? These are the number of values of x that are possible. So for that, I mean, what was even asked in the question, I went with the flow and we calculated this, but okay, we are asked to find the maximum value, right? So what you will observe, like if you are given a k value, okay, so and we know the formula for g of p comma q, you can calculate it. It varies, like let's say the minimum value of p is given by this one, this, right? Minimum value of p is minimum of n minus k or k. Sorry, sorry, I'm really sorry about it. Minimum value of p, because x was equals to b, minimum value of p is given by this equation. Like it can go, it can be 0 or it can be n minus 2k. So let's say you are here, let's try to draw a number line. So let's say this is the minimum value of x, so it can be maximum of 0 or m minus 2k, right? And let's say you have a maximum value here, and yeah, it will be maximum of minimum of n minus k comma k, right? So let's say if you put p equals to this value, you will get this score. Then let's say your value will first increase for some point, and then it will continuously decrease, right? So because this is a summation function, this is not that much complicated. This here is a summation function, so it will first increase and then it will decrease only. So yeah, I mean, actually I don't really know how to prove it, but in general this kind of questions you generally have a convex function. So this is some kind of convex function. Okay, so it will first increase and then decrease, and that is why I mean, it can actually go, it is not like it will happen maximum at the middle point only. It can happen like this, goes like this, so it will be very close to the minimum value, or it can happen like it first increase and then it decrease dramatically, so the maximum point was very close to the max value. It is not necessary that it will be happen at the middle, right? So for these kind of questions, what you need to do is you need to apply ternary search. Right, and using ternary search you should be able to find this point where the maximum value was occurring in big O of log n time, right? So basically the range of this big O log n of this range. So you should be able to find this in big O of log n time using ternary search. Just read something about in Wikipedia. I think most of you will be familiar with binary search, and if this is your first problem, yeah, that was a prerequisite. I forgot to mention about that. But basically you have something and you have a convex function. If you want to find the maximum value in this range, the maximum value of a function or the value of x where a function is getting maximized, you can apply ternary search on integer. Okay, so there are a lot of blocks on how you can do it on double, but you need to find the way to do this on integers. Okay, so once you have done this on integers, you should be able to find like this. And how do you know how many k values are there? You can just start iterating from k equals to 1 till infinity, and whenever, like if this range like x min x is also 0 and max is also 0, or if the max is like when this set becomes 5, you can stop like that. So that was the whole solution for this. I hope you were able to understand this. Let's actually see it in code. Let's see. So first of all, I am taking the integer, the two arrays ai and bi, and I'm sorting them, so it is already n log n time. And yeah, we have an answer array because I don't really know how many k values will be there. So yeah, I'm starting with k as 1, and this is the answer. Now to query the sigma, like if you see the function g function, yeah, so we have this g function here, and clearly it takes big O of n time to calculate. So for that we can actually maintain a prefix a and prefix b array, and like I'm storing it in a way that prefix of I will give me the sum like this. So prefix of p minus 1 plus prefix of n minus p minus n, like that. And yeah, actually this is not the f function, this is the g function, but you can actually reduce it. Like if you have this as p is x, then q is already k minus x, right? So if p is x, then q is k minus x, and obviously there are some constraint, like if both are less than 0, then it doesn't really make sense to do anything. If and also the value of p is at most half, right? Because if you like if the p is greater than half of this the number that we have here, it doesn't really make sense to actually do these operations, right? Yeah, so with that, it doesn't really make sense to actually do these operations. So I did some kind of like that. I just eliminated the possibility that will never actually happen. So yeah, you can actually just calculate the the scores and then just add them and return. and this is the template simply for the ternary search, like from here to here. So this is the maximum value 2k minus m, and this is the minimum value, and just try to do a ternary search over this range and find the and generally the answer is in low plus 1. So score low and score high, and yeah, you can just push the maximum of these two scores. So that was the ternary search, and then just do a k plus plus. So, and whenever the low is greater than high, you can break out of this loop. So the size of the answer will be the number of k values, and you can just print it. So I hope you were able to understand this. Let's move on to the last problem. Yeah. Okay. So this is a tree problem, and you should have some knowledge of. You should know how to calculate lowest common ancestors. That is a prerequisite. Other than that, I don't think there is any other prerequisite. So let's first read the problem statement. You are given a rooted tree containing n vertices rooted at vertex 1. A pair of vertices u and v is called a good pair if u is not an ancestor of v and v is not an ancestor of u. For any two vertices, distance of uv is defined as the number of edges of unique simple paths from u to v, and LCA is defined as the lowest common ancestor. So these are the basic definitions. And a function f of uv is defined as follows. So f of uv is the number of distinct integer x such that there are non-degenerate triangles formed by side length this. Okay, and we just need to calculate this. So it is a very small problem statement. Let's just go over the test cases. So yeah, so we have 3 1 2 1 3. So 3 we have 1 2 and 1 3. So the number of triangles, like this is like only one pair is possible, 3 and 2, and LCA is 1. So if you have a triangle of side 1 comma 1, how many integers would you be able to generate? Like there is only one possibility, you can't even make 2, right? So that is why I think the answer should be 1 here. Yeah, and in this case 3 1 and 3 2. So if you have 1 2 and 3, every pair is ancestor of other, so you will never be able to form a triangle. So that is why the answer is 0. If you have 1 2 1 5 4 2 and 1 2, so we have a tree rooted at 1, and we have 1 2 1 5, mm, 2 3 and 3 4. I think that is the tree. So okay, let's try to think about this. For if I select like for node 1, there are the contribution to the answer will be 0, obviously, right? For node 2, we can use this as use 5 as a pair. So 2 5, that will contribute 1 to the answer. Okay, 1, because side of 1 comma 1 will have a maximum of 1, right? For nothing else. For 3 and 4 can contribute to the answer, so plus 1. Then 3 and 5. Okay, so if you have a side length of 2 and a side length of 1, what can be the range of x? So in here x can't be 1. The only possible possibility x equals to 2, nothing else, right? So that will also increase my answer by 1. For node 4, only 4 and 5, so this is the same, it will do a plus 1 contribution, so 1 2 3 and 4. So yeah, that was the sample test case, and we have an answer of 4. I can't really discuss this like that. Okay, so let's see what is asked. For any pair, f of u and v is the number of non-degenerate triangles that can be formed. And clearly, okay, So let's say we have an LCA of two vertices. You have a node U. You also have a node V. Okay, so this is at distance A and this is a distance B. So it is saying like we have a triangle basically, and this is a and this is B, and this is a triangle of side X, right? And we need to find the number of pairs. Sorry, the number of integral values of X that are possible. That is the answer for F. So how can we actually do this? So if you know the triangle inequalities, what are they? So we have A plus X is greater than B, A plus B is greater than X, and B plus X is greater than B plus X is greater than A, right? So let's try to find out the value of X from each of these. So if you do that, X is greater than B minus A, X is less than A plus B, and X is greater than A minus B. So clearly if we say if we just normalize it, let's say B is always greater than equals to A, or I think we can do it in some other way. Let's say capital M equals to max of A comma B, and small m is equals to min of A comma B. What you will see is that X is less than capital M and X is greater than small m, right? Yeah. Not exactly. Wait, let me think about this. Okay. Okay, so if we have this, what can we do about it? Since X is if you think about this, X is less than B minus A, and it is less than A plus B, right? So let's try to put the values. This actually here is B minus A is actually M minus M, right? Less than X less than A plus B is M plus M, small m. And if you actually go for equal to range, so that will be like M minus M plus 1 less than equals to X less than equals to M plus M minus 1. So the total number of values if you calculate, that will be equals to R minus L plus 1. So it will be equals to R minus L, so M and M cancels out, 2M minus 2 plus 1, which is equals to 2M plus 1. Okay, so the total number of values is equals to 2 times the minimum of A comma B plus 1, right? Yeah. So we have this equation from if you are given two sides of A and B, the total number of values that are possible are simply this. Now okay, what can we do about it now? This is if you are given A and B. Like whenever we are trying to solve the question, we don't really have this A and B at our hand. We generally have, like, let's say this is depth of L, this is depth of U, and this is depth of V, right? So clearly A will be du minus dl, B will be equals to dv minus dl, and if I put these values in here, what will we have? The number of values, let's call it hashtag V, is equals to 2 times minimum of dv minus du comma du minus sorry about that, I wrote it wrong, dv minus dl minus comma du minus dl plus 1, right? And since this is common, you can actually take it out. Was it plus 1 or minus 1? I think it should be minus 1, not plus 1. I think I made a mistake here. Sorry about that. So yeah, it should be minus 1 here. Very silly of me. No. If we open up this bracket, how much will we get? We will get 2 times minimum of dv and du. So du comma dv, and these two will be added. So I can take like 2 times dl plus 1. This one also should be a minus sign. Yeah. So this is the total final number of this is my final values. I can just do it for all pairs. Do this for all pairs, and you will be able to calculate your answer. But if you see, like, you can't actually do this for all your pairs because n is going till 10 to the power 5, right? So since n is till 10 to the power 5, this will give you a TLE, right? So let's see how we can actually go about it further. Okay, so what we can do is we can try calculating this part separately. Okay, so what we will do is first of all we will try to calculate this part separately, and then we will try to calculate this part. Okay, so let's say this is hashtag 1 and this is hashtag 2. Okay, let's try to study about hashtag 1. So what we want to calculate is 2 times d minimum of du comma dv, and this pair of sum, actually we want to do it for all the nodes, right? Like that, for all u comma v we want to do it. Let me let's say, how do I even explain this? Let's say we have a tree 1 2 3. Let's make a complete tree only. 4 5 6 and 7, right? Let's say you have a tree like this. Now if you want to calculate like let's say for node 2, what do we really need? Like we don't want to consider these two elements, we want to consider this. And let's say if there was one more child, 8 9 and 10, we also want to get the subtree size of this subtree, right? So that is like what it is. This is not easy to maintain with only depth. So you can also store the subtree size of each node. So let me just make that thing again. 8 9 and 10. So clearly what we'll have is how many nodes are at the depth. So let's say one is at depth of 0, this is at 1, this is at 2. So these all nodes are at depth of 2. These all nodes will be at depth of 1, and yeah. And you can also have a map of how count of depth, like how many nodes of depth 2 are there, how many nodes of depth 1 are there, how many nodes of depth 0 are there. So let's say depth count is like depth of 0 is 1 node at depth of 0, 3 nodes have depth of 1, and like 1 2 3 4 5 6 nodes at depth of 2, right? So now if you query how many nodes are of depth x, of depth greater than equals to x are there, so you can just take the prefix sum. So the number of nodes with depth greater than equals to 0 are 3 6 9 10, right? The number of nodes with depth greater than equals to 1 are 9. The number of nodes with depth greater than equals to 2 are 2. So this is like the prefix sum of this. So we can clearly maintain the number of nodes and handle queries like the number of nodes greater than equals to this. So if you are asked like what is the number of nodes that have depth greater than equals to d, you can make this array and try to query this in big of 1, right? So yeah, so if you have like if you know, like for 2 you want to know this value. So let's say I set the d min is equals to depth of node, right? So you can just get the number of nodes that have depth greater than equals to 1, that is 9 in this case. So 1 2 3 4 5 6 7 8 9. So you have 9, but I don't really want to apply this for these this subtree here. So the subtree size actually, sorry, I wrote it wrong here. The subtree size should be 3 in this case, 3 in this case, and 3 in this case, not like this. Okay, so some error code. Let's continue. We were at like if depth, the minimum depth. Let's say. Okay, so if I set the minimum depth as the depth of current node, I don't really want to consider these 3 elements that are the size of this subtree. So let's say it is 3. So I don't want to consider 3 elements. So if I say like the number of nodes that have depth greater than equals to 3 are 9 minus the subtree size, that is 3, I will get 6 nodes, which are these, right? And for these 6 nodes, the minimum depth is 2. Okay, sorry, the minimum depth will be 1 because this is our depth of 1, right? So I can easily say that we can actually easily calculate it in big O of 1 time as depth of node, let's say it is node u, times the number of nodes that have nodes with greater than equals to d of u, right, minus subtree size of node of u. So we have this so we have this kind of thing, and this is equals to like what did we actually want? We wanted 2 times min of this, right? So this is the number of pairs that we will have for this node, and we can actually multiply it with 2, right? And we can sum this up. But okay, so let's say you did this. Now you have a lot of a very big sum now. But what happened was, let's say you had a node 1 and you had a node 2 and you had node 3. So when you do this for all the nodes, this will contribute 0, but okay, this number will contribute a 1, and this number will contribute a 1, right? Sorry, not 1, since these are at depth of 0, 1 and 1, so this will contribute 2 times 1 times 1, plus for 3 it will contribute 2 times 1 times 1, right? This will give you an answer of 4. So basically for 2 and 3 it was computed twice. We only wanted to contribute for every pair, but for every pair it was contributed for every pair at the same depth. For every pair at the same depth, this was added twice, right? Like if you see this tree, I'm going okay, let me use some other pen. So for 2 and 3 it will be counted twice, but for 2 and 6 it will be counted only once, because when I reach at 6, 2 will not be at the same depth, so we will not be considering it one more time, right? Okay, so how do we actually handle this? So since we had 2 times, okay, let's use the different color. Since we had added this twice, what we can do, like the number of pairs will clearly be like, let's get the number of nodes at the same depth. Like we had this array, right? So the number of nodes at depth 1 is 3, the number of nodes at depth 2 is 6, right? So let's talk about this only. So the number of nodes at depth 2 was 6. So in reality what I wanted was nc2, like the number of nodes at depth 6 would be 6c2 times 2 times minimum of like the minimum of sorry, what am I doing now? Okay, one more thing, like you might ask, like why can't we just go level by level and just add nc2 and that? Because then we will not be considering these cross pairs. You will only be considering the pairs of these and this and this. That is why what we are doing is, first we are calculating it for all the nodes, and then we are subtracting the extra added for every level. So for every level, what the extra that was added was NC2 times 2 times the minimum depth. That was the depth of node, the current depth, right? So you can go from level 0 to a maximum level, and for every level you need to calculate the number of pairs at level. This is basically the number of pairs at each level into 2, so it will be equals to n into n minus 1 times depth. So basically you will need to subtract this from your answer. So first of all, what you do is you need to do plus equals to this value, and that you can do easily in big O of n time. This you can do in big O of max depth, and max depth can, in worst case, it will be big O of n time. Okay, and now you still have to calculate the other value, that was this part, right? The hashtag 2 times dl plus 1. Okay, now for this value, let's say you have a node. Let's say this node, it has a lot of children. Let's say it has subtree size of s1, this has subtree size of s2. So clearly the number of pairs that can have this as the LCA will be, basically what we want to do is we want to add 2 times dl, the depth of this is dl plus 1 times the number of pairs of children that this has, such that this is the LCA of that. So this number of pairs, if you want to calculate, it is equals to s1 into s2, right? But let's say you have more number of children. Let's say you have more than one children. What will happen? Let's say we add one more children, s3. So it is equals to s1 into s2 plus s3 plus s2 into s1 plus s3 plus s3 into s1 plus s2, right? And this is equals to 2 times s1 s2 plus s2 s3 plus s1 s3 s1, right? Okay, so I think you already see a pattern. Like when there were only 2 children, we the sum that we had was s1 into s2 plus s2 into s1. I mean, there were 2 kinds of pairs that we had. Actually, it is not 2 times like this. Let me just think about this. Yeah, it will be divided by 2. Sorry, this number will be divided by 2, right? Because we are considering s1 and s2, then we are considering s3 and s1 also. So this number should be divided by 2. Let me erase it. Okay, now the total number of pairs is, one pair is s1 s3, one pair is s2 s3, and one pair is s1 s3 s1 s2 s3 and s1 s2. Okay, so these are the number of pairs. Now what you can do is you can multiply this by 2. If there were only 2 children, you had s1 s2. If you had more than 1 children, then you had like this. And it is a very common formula that you can follow, that a1 plus a2 plus a3 till an whole square is equals to summation ai square minus 2 times the sum of pairs, right? Actually not plus, it is minus. So the sum of pairs of every children, like if you want to calculate the sum of pairs, what you can do is you can first get the summation ai and square it. Basically the size of these subtrees, you can just square it, take the sum and square it, and from it subtract the summation of si square, like this, and you can divide this by 2. That will give you this kind of value. Okay, and once you have this kind of value, you can just do it like 2 times dl plus 1 times sum of multiplication of the pairs. and just subtract this and you will have your final answer. So that was the code, that was the explanation, and let's see the code and finish this video. Okay, so let's say you have a graph of max depth, and yeah, you can actually like this is the depth. Now we just run a readyFS from node 1, and this will calculate the parent of each node, the depth of each node, and like the depth count, how many of nodes have this depth, right? And I'm also maintaining a maximum that we have. You can just assume it to be n-1, that will also pass all of your test cases. And yeah, and then we can maintain a prefix sum to get the maximum, the number of nodes that have at least this depth. And for every pair of depth, you can we did this, like we had this formula. Yeah, this one, 2 times depth of node into this one, the number of nodes that have this at least this depth minus the subtree size of a node. So the number of the number of nodes that have this depth minus subtree size of node. From this, first I need to remove this part, like how many nodes have this exact depth, and we can remove this from the answer. After that, I need to calculate the sum of squares and subtract it, and then we can remove it from the answer. And that's it. That is it for the solution. Okay, so that concludes the video. If you are able to understand this, kindly like this video, subscribe to the channel. I will see you guys next time. Thank you.